Hi, this is Ethan Poole, student ID 2303499, and I'm going to be discussing public key encryption and digital signatures lab. The first task asks questions around prime number generation. The reason prime numbers are crucial in cryptography is because a big prime number is hard to defactorize compared to a non-prime number. In general, when two large prime numbers are multiplied, it is a lot harder to find the result, making them more secure. Putting this into my VS Code, it will generate two prime numbers within this set range. As you can see, it's come up with two prime numbers, P and Q, within these ranges. If I change the maximum parameter, there is a larger range, especially if the minimum parameter is lower, which would make the prime numbers a lot harder to guess. These two prime numbers are now less likely to be the same number, so if I just run this now. So this code right here will calculate the GCD of two numbers. The GCD of these two numbers is 6. I've now added my own code to check if the two numbers are coprime. So Euler's totient means the amount of coprime numbers less than n that are coprime to it. So using Euler's totient, it's possible to see the amount of potential values. If I then add in the Euler's totient code that was on the lab sheet, just under my explanation, into the prime number generator, as you can see, I have put the exponent code to find an exponent with the prime number generator, greatest common divisor, and also the Euler's totient. This code will make sure that an exponent is found. So as you can see, I have added the RSA key generation. I have correctly linked all my code together. So now, as you can see, I've imported my encryption functions. So my encryption function is there. If I run this, see, it encrypts there. As you can see, I have implemented the decryption in this code. So the message there is hi. Yeah, decrypted message is hi. But what I've noticed is if I raise the amount of characters used, then I undergo an issue where the message is too large for the key size. Now I'll move on to talk about digital signatures using RSA. So digital signatures verify that a message was from the authentic sender and that nobody else has altered anything. The signature is created with RSA by encrypting a message hash using the original sender's private keys, and the receiver can verify this with the original public key. So as you can see, this has officially signed the message using the private key, and then this is tested to ensure that the signature is printed. It is very important to use a private key for sign-in because it belongs to the authentic creator, and so it is unique to them. So if the recipient sees the signature, then they know that it was sent from the correct person. If this fails, then they will know that it has been tampered with or altered with during transmission or has not been sent from the correct sender. So the private key is used as it is unique to the original creator. So as you can see, I've put the verifying signature code from the lab sheet underneath my sign-in code. This uses the public key to authenticate that this was created by the original owner from the private key. The signature is true. If I change the message slightly, so you can see I've changed the message from hi to IH and run this, I still get a valid signature. And this is because the same private key is still used to create the signature and the same public key is still used to try and verify the signature. So it's still authentic. So the original verification works, so I then modified a public key. So I put it to wrong public key, and what I did is I essentially added 1 to n, and then I've ran another verification to check. As you can see, signature with a different public key, false. It'll be an invalid signature. Basically, the sign-in process is like an opposite to encryption, as during encryption the public key can encrypt, but the private key has to decrypt, whereas sign-in uses the private key to sign in the first place, and public key is used to verify this. And then we move on to why is message integrity important in digital communication. So message integrity is important to ensure that a sender is authentic and that a message has not been altered without permission or anything changed during transmission. I will now use the following command to generate a private key in RSA. Using the cat command, I can now inspect this. After using the cat command, I can see that all types of typable characters are used. So caps lock letters, non-caps lock letters, numbers, and also symbols. Using this next command, I will generate the public key. So this is then generating the public key. I'm also going to say how important it is to keep the private key secure, because this is the only way to decrypt and sign. If this is not secure, anybody could tamper with the message as well as view it without permission. The next command will create a message and put the text into it. Now, using the previously generated public key, I can use this command to encrypt the message. Now, to view this encrypted message in a binary reader, I would use XXD. As you can see, it shows it's represented. As you can see though, this essentially looks random. It just shows it's been encrypted and it's unreadable. I will now use a command to decrypt the message. As you can see, after running cat decryptedmessage.txt, it displays the text of the message. This is a secret message. If I did this without using decryption, I would not have the same result. As you can see from this command, I've now signed my message, and signing the message ensures the authenticity. As you can see, I've now used this command to verify that it has been signed, and it has. If the message was altered before verification, the decrypted hash will not match the new hash. And now to answer these questions as a summary. So OpenSSL is better than generating everything from scratch, as it is a tested official platform, whereas doing this by hand could lead to accidentally creating flaws and also vulnerabilities. And now to answer this last question. So Python signatures are made with implemented steps, whereas OpenSSL does sign-in and verification in an abstracted format, which is seen as more practical, but less can be seen under the hood, as in the code itself it gives more of an insight. Thank you very much.